Throughout this first sequence of explanations, we've been laying out the pieces of a puzzle. First, we introduced the Standard Model. This constitutes the set of fundamental particles used to build all matter and the different ways these particles can interact through the three Standard Model forces: electromagnetism, strong, and weak. Next, we discussed the theory of classical mechanics, which revolved around two central objects, the action and the Lagrangian. We determined that the action represented a rule for how nature tends to evolve over time. That is, nature tends to transition in such a way as to minimize the amount of action that it expends. In order to make this decision, we noted that nature uses the Lagrangian, which is the difference between the kinetic and potential energy of a system, as a sort of GPS, illuminating the path of least action. Finally, we saw how in the world of quantum mechanics, state transitions cease to be completely deterministic. Thus, we are not able to discuss the exact way a system will go from state A to state B, but rather must analyze the probability that such a transition would occur. We determined through the principle of superposition that this probability could be calculated by taking the path integral, that is, the sum over all the different ways the transition from A to B could be achieved, with each way being represented by a probability wave with a phase factor proportionate to the action required to make its particular transition. At this point, it might not be totally clear how each of these puzzle pieces fit together. This is a perfect example of something which happens somewhat frequently in the study of physics. We have an answer, or a set of answers, but we don't know exactly to what question. It turns out, the question that these answers answer is what might be considered the ultimate question in all of physics. That is, given a set of particles in some initial state I, what is the probability of finding those particles in some final state F after allowing them to interact with each other and the environment over some period of time? Putting together our puzzle pieces, we can construct a very simple recipe for answering this question. First, define the initial state I and the final state F of interest by identifying the Standard Model particles present in each state. Indicate the trajectories of each particle to establish the kinetic energy associated with each state. Second, determine all the possible ways these particles could interact with each other or the environment through the Standard Model forces on the way from state I to state F. Associated with each interaction is a potential energy and a messenger Standard Model particle connecting the initial and final state. Third, using the kinetic energy associated with the particle trajectories and the potential energy associated with the particle interactions, form the Lagrangian kinetic energy minus potential energy of each possible transition mode. Fourth, from the Lagrangian, calculate the action required to make each transition. This is directly proportionate to the phase of the probability wave associated with that transition possibility. Finally, compute the path integral by taking the sum over the probability waves associated with each transition. Since effectively every physical system is composed from some combination of Standard Model particles which interact via the Standard Model forces, this recipe constitutes a method for analyzing effectively every physical system in nature. But it gets even better. The great Richard Feynman, to who we owe the path integral formulation of quantum mechanics, among his many great contributions to the field of theoretical physics, developed an ingenious technique for representing our recipe with nothing more than a few pictures. This technique is now called the Feynman diagram and is one of the most widely used methods for communicating and doing physics. Simply put, the Feynman diagram is comprised of four parts. The canvas upon which the Feynman diagram is drawn represents a coordinate system, with the x-axis typically denoting space and the y-axis typically denoting time. At the bottom of the diagram, corresponding to the beginning of time, we draw the initial state of the system. At the top of the diagram, corresponding to the end of time, we draw the final state of the system. The trajectory of the particles in each state is then depicted through straight lines, which encapsulate the kinetic energy of the system in terms of the motion of the particles through space. Where these straight lines meet, we think of the particles as interacting. These points are called the vertices. Associated with each vertex is an interaction potential energy. Finally, the system is brought from the initial state to the final state by the intermediary of a messenger particle, which facilitates the interaction. The messenger particle is denoted by its own line. Once a Feynman diagram is drawn, it can be translated directly into a path integral using what are called the Feynman rules. Strictly speaking, these rules tell us how to form the initial and final particle states, the interaction Lagrangian, and the messenger particle operators, which come together to form the path integral. Intuitively, however, we can understand this procedure by recognizing each piece of the Feynman diagram as relaying a mathematical object, the product of which results in the path integral. Thus, the pieces of our puzzle quite literally come together to form the Feynman diagram, which constitutes a symbolic solution to our ultimate question. It is a triumph of epic proportions, to be sure. Quantum field theory, the edifice within which the Feynman diagram is applied, is quite rightly considered the most accurate and successful theory in all of science. However, to close, I must warn that despite how it may seem, the puzzle is not yet complete. The Standard Model, for all its success, is riddled with missing pieces. Now, with our foundation set, we are prepared to enter the great unknown and confront the riddles of contemporary physics head-on.